Hello and welcome to this session. My name is Thomas Zwölfer. I'm with the Esri R&D Center in Stuttgart. And today's topic is going to be integrated mesh production with Shure. Creating technology and software with a focus of being able to create integrated meshes in a very precise and efficient manner for countrywide and professional mapping applications has been at the core of our work for the past years. And it's actually a great honor and pleasure to be able to present this work to you today on the Esri Developer Summit in 2021. I really hope that you can get inspired from this talk. It's actually quite a pleasure of representing also our team today. We have become part of Esri in the middle of last year, and we're excited to be part of the family, and we're excited also to contribute and to showcase that today. Our colorful team has something in common. This is a common passion for transferring cutting-edge research from photogrammetry, computer vision and machine learning to software for large-scale mapping applications. These are our talking points for the session today. First, we're going to have a look at how Shure is actually positioned in the ArcGIS ecosystems and how it interacts with other products from Esri. Then we're going to focus on the integrated mesh generation itself, so the process and the technology that comes with the task of creating a 3D mesh from images. Next, we're going to focus on the challenge of making integrated mesh accessible to everyone at every time possible. And in the end, we're going to have a look at use cases, what people actually do with the meshes, how they create value, what are the applications that can already be performed using integrated meshes today. So our first topic will be the software technology Shure. So this is the software and technology that we've produced in the past years for automated data production for mapping and 3D. And this slide shows how Shure is actually positioned within the ArcGIS system. So it actually represents the link from the input data, which can be images, which are LiDAR, and also orientation data coming from area triangulation packages. And they can be used within Shure to actually produce DSM orthophotos, point clouds, digital surface models, and also textured meshes. And those textured meshes are going to be the main topic of today. And all of these output products, they can then be used in ArcGIS, be it in Pro, be it in Enterprise and online, and then can be used for various applications, be it mapping in the classic sense, for 3D visualization, change detection and surface analysis. Also simulation applications and use cases come to mind. Later I will also show some use cases that come from this direction. And we've actually taken care that the software is on the one hand fast, it produces highly accurate results, it's massively scalable, that means it can produce data from, let's say, very small data sets that maybe just focus on a construction site, up to countrywide mapping, which is actually our specialty. On the one hand, on the other side, of course, in a very cost-effective and fast manner. For Shure, we have created a variety of deployment options. Now, on the left, we see actually its deployment as desktop software, so that means it can be used in consumer-grade hardware, ranging from standard laptops to standard workstations. But for more professional productions, we see it actually deployed more and more on server hardware, where it actually can be used via its command line interface for remote processing. And of course, this also enables scripting and therefore even a higher degree of automation. Now these days, the amount of data, so the amount of imagery gets bigger and bigger, so the projects get bigger. On the other hand side, the time to delivery for these projects gets smaller and smaller, so it's very important to be able to scale beyond the point of what's possible in one single processing workstation or even server, but basically to go beyond that and split up the work between a number of processing nodes that are set up in a cluster. And we see this often that dedicated clusters are set up, Shure is being deployed on those, and work can be scaled up very efficiently, so time to delivery can be reduced significantly. For even more flexibility, Show can be part of SaaS offerings in a virtual cloud environment. And this is of course interesting because here the load that is necessary to be processed can be scaled elastically within this environment. A particular area of interest of a city, for example here, if like from Frankfurt am Main in Germany, you can actually specify the region of interest via shapefile, and that means that we will only produce data that actually falls within that shapefile, and we will not waste any processing time or produce redundant data that doesn't fall inside of this particular region of interest. On the other hand, we can feed water shapefiles to Show to tell the software where in fact there is water, so where we can actually also treat the data in a different manner because we already know that it's water, and we will create clean looking water surfaces from this shapefile information that is fed beforehand. As the next steps, we split up this area into an automatic tiling for efficient processing. That means we process each tile by tile, and in that manner we can actually be scalable towards basically an unlimited size of data sets. That also means that this is a means for splitting the work in between different machines. That means one particular machine can actually work on one particular tile, so we can actually finish with the whole area even faster. The results of this would be a consistent digital surface model here as an example for this particular region of interest that you will get in a tiled manner, just with a regular geotiff output, perfect for further processing within a GIS system. Here we can see a DSM orthophoto that will also be cut and produced for this area that can directly be used in your GIS system. And also in a fully automatic manner, we can derive 3D meshes. And the rest of this talk is going to be focused on this 3D mesh product, what makes it special and how it is being created. Why are meshes so powerful? They can serve as a link between spatial data, as they integrate both 3D geometry and full resolution texture. They can be produced fully automatically, and therefore also models or data sets that consist out of meshes can be produced completely automatically and updated very fast. They actually empower intuitive interaction through the photorealistic experience, meaning that even non-specialists can consume geodata on any device with meshes. Their multimodality is created by linking mapping data from very different mapping platforms and on very different scales, meaning on a global scale with satellites, all the way through airplanes, drones, mobile and terrestrial photographs, all the way down to the very local scenery. And all of this can be created in one single mesh model. They can be used for a variety of use cases, such for example as access to metadata and semantics through the mesh. So the mesh serves as a canvas for even other types of objects and GIS queries. Now I want to go into the actual 3 steps that make up the generation of meshes. On the one hand, we have the point cloud generation, then the mesh surface generation, and as a third step, the texture generation. During the point cloud generation, we reconstruct for each and every pixel in the input imagery as a 3D point. And if you think about it, if the input data set has 10,000 images, we are actually talking about terapixel of input images that will actually create points. So that means this will create a massive amount of data. And we can use this redundancy in data and exploit it to really create very clean point clouds with sharp edges, with distinct roof lines, and with very low noise level, and with a very reduced data sets by filtering stage, taking into account all of the redundant data that we have in our input. Now, while these point clouds actually are already an output and already a product that are used and their use is widespread, they serve as an input themselves for the creation and for the mesh surface extraction. And for this, we actually take the point clouds and we try to find a surface that actually connects the individual vertices of the point clouds. If we find the surface, we create a topology. So we create a meshed surface out of these points and we optimize this topology. We want to retain geometric features, we want to retain geometric detail, sharp edges, distinct building features, smooth and straight facades and ridge lines. And these are all surface properties where we optimize our mesh surface for. At the same time, we can also reduce the amount of geometric data because now we can actually represent a plane that has to be represented with hundreds to thousands of points to actually be visible as a plane by a single or by a very low number of mesh faces. So therefore we actually have a compression of data by using the mesh representation instead of the point representation. Now, as you see on the left side, now we do have a mesh surface, but its actual power really comes into play when we apply a texture on top of these meshes. And for that, we actually go back to the input imagery and we take the full resolution and we put these images back onto the mesh. We drape it on top of the mesh. And what that means is that we can actually guarantee that for each and every point in the mesh, we have the optimal input image, and the part of the optimal input image that has that locally highest resolution glued on top of the mesh. So we create this photorealistic, very high resolution texture. On top of that, we do a global color adjustment for a consistent and for a vibrant look all across the data set. Here, for example, you see a data set that we have recently processed that had been captured with the Leica CityMapper 2. And we can see here the city of Munich, and we can see the mesh geometry. And this is already, it's a very nice data set that could be retrieved there, but it just becomes so much more when we apply the texture on it. It just looks so much more photorealistic and more graphic. Now, once these meshes are created, they're basically created at the place where the software is run now. As I said before, this could be a workstation in an office of somebody who actually produces this, or this could be on a cluster, but it's actually not the place where meshes are supposed to be used. The meshes actually get their real power when they're used with a consumer, with an end customer. So the question is, how can we actually make this integrated mesh accessible to consumers? And the key here is we do not want to make mesh available that's, maybe ranging in a scale for 1 square kilometers. Actually, 10 square kilometers is also not enough. We're dealing with data sets that go up much more. For example, here is a different data set where we actually have 47,000 images that have a total resolution of 4 terapixel and that make up an area of 450 square kilometers. Now, the question, and of course this is actually a huge amount of data that is on the one hand going into the software, but of course also coming out of the software. And now here the challenge is, how can we make this type of data available to a consumer who maybe only has a handheld device such as a mobile phone? Summing up, what are the challenges? How to deal with massive scale and increasing resolution in countrywide data sets. That means we're currently seeing data sets with thousands of images ranging for a high number of square kilometers that actually go down in resolution down to 2 centimeters of resolution, for example. And this actually gets smaller and smaller. Now, and how can we make this data readily available for everybody, everywhere? That means not just on a workstation where the mesh is being created, but really everybody wants immediate access and can have immediate access to this data. And we do not just want to have it working and being navigatable on a workstation, but we also want to have it navigatable on a smartphone. We recommend our customers to actually create the SLPK i3S output format, since it's very well suited to overcome these challenges and actually to make these meshes available to the end consumers in a very efficient manner. And we also recommend that the meshes be hosted in the cloud so that it can be consumed everywhere at any given time. The i3S format itself has actually been designed for rapid streaming of 3D data. And this makes it inherently different from traditional mesh formats like, for example, OBJ. It has and can support the level of detail structure. That means the mesh is actually not a single file, but rather a tree of files where each level in this tree actually represents a different level of resolution. And this actually makes it possible to stream large amounts of data countrywide meshes at one time in one view, as can be seen on the left side. It is a free format. It has its own OGC community standard. Therefore, it's also something, its implementation can be looked at, and you can build upon it and you can implement the export yourself. In its latest 1.7 standard, it offers support for Draco compression, which is a state-of-the-art geometry compression algorithm, where the mesh geometry can actually be reduced so much and compressed so much that the traffic that's necessary to transfer the meshes from the web to the device is limited by a lot. Also, node paging and client-server traffic is reduced by the efficient implementation of the tree that makes up this level of detailed data structure. It is also fully backward compatible. That means you can really build your systems on top of it and can still expect meshes that are already quite some time old to still be compatible and to still work out of the box. This also means that it can work across all platforms. That means, be it an Android smartphone or a workstation, we can always utilize i3S and access those meshes even via the browser. On the next slides, I'm going to be talking about the level of detail structure that makes up the core of what makes i3S so powerful. On the left side, you see a full resolution representation of the mesh with its wireframe, and what you can see is there's really a high number of triangles that make up the surface. Now, this is already a lot less data than it being represented by points. However, we do not only carry the geometrical information of the faces, but we also carry the high resolution texture from the input images. On the one hand, this makes it really vibrant and more detailed looking and really gives it a high resolution look. On the other hand side, this data is very heavy. And in order to really enable efficient streaming and to actually display huge amounts of data, we need to create a representation of the same surface that is has much less data size, while preserving actually the most distinct and significant features of the model. And we do this by both simplifying the geometry and also the radiometry through different levels. As you can see in the middle, this would be the first simplification of the model, where we already see that there's just a much lower number of triangles, and also the texture resolution has been minimized and downsampled by a lot. What this means is that this is a much more lightweight representation of the same mesh. So that means at one time, if we want to see a bigger part of the mesh, we can load much more of this data density than we can load from on the left side. On the right side, that would be the next level simplification of the same data set. And as you can think about that, this is again has a much lower amount of data that needs to be transferred to be displayed. That means we can display a lot more of this type of mesh. Summing up, we create from the very same part of the mesh a variety of different versions. Each is actually reduced in data size, so it's actually a very smaller file, and also in geometric and texture resolutions. And what we then do is we put these different files in a tree data structure that's structured like that. Now, if we start from the top of the tree, we actually have basically a very zoomed out version of the model. We want to be able to load all of this overview with a very low amount of data that has to be streamed to our smartphones. That means this level needs to be really generalized a lot, and it needs to still look very much similar and the same as the high resolution model, but it just has to have a lot less data for it to be streamed efficiently. Now, once we zoom into the next level, so the one below, we already load the next level of detail. That means we now can see more geometric detail, we see more high resolution radiometry or texture, but we also need to load just a smaller portion of the mesh. So that part of the mesh also can have a bit of a more data size. It still needs to load efficient, but we can now and want to now see more of this data. As we move closer, we again want to actually load more geometric detail. Now we want to zoom up close, and we really want to be able to see the minute details of the model, and therefore also have the full radiometric resolution. As we move out, so as we move up the tree with the viewing distance, also the streaming speed needs to increase. That means we need to be able to stream a lot more of the environment, a lot more of the model in a faster time. And this also, and to put the data in the tree like that, and also create the transitions between the different level fluent, so that the user actually does not recognize that something changes in the model. That actually really is the challenge in creating this level of detail, but also is something that's very much empowered and supported well by what I3S is and what it represents, and also by all the algorithms that I3S also supports. For example, the Draco compression really helps to create very small geometry in those mesh files. It's even possible to view and to stream meshes that have been created from whole countries, such as the next video that's going to show you a mesh that has been produced with Shure out of the whole country of Luxembourg, and it can be streamed onto your smartphone via the web very fluently. In the first part of the presentation, we talked about the process of creating meshes from images by creating point clouds and then deriving surfaces from those, while subsequently creating textures. The second part of the presentation talked about what to do to make meshes actually available to everybody. And in the last part of the presentation, we're going to look at use cases of what people actually do, what users actually do when the meshes are available to them, and what type of value can be created with those. The first use case is telecommunications planning. Now, as meshes are a surface, they are very well suited for simulation of the propagation of waves. And this actually comes in very handy if we're looking into urban 5G planning, and where wave propagation planning and prediction of such waves is very crucial. Here meshes are being loaded, and then here we can see even that obstructions can be simulated, and so the planning and the positioning of the posts and of the antennas where the 5G network is being created can be planned very efficiently based on mesh information. The second use case I want to show here is a flooding demo. Here we see a scenario where the River Main in Frankfurt in Germany actually is flooded, and we see what parts of the city are being affected by it. And as this is really 3D data, and here again surface data, flooding can be predicted and can be simulated in a very efficient manner, so we can stay one step ahead and we can plan one step ahead and go for security measures before the flood actually takes place. Another use case of integrated meshes in ArcGIS Online is the newly developed clipping and masking functionality, which actually allows you to clip out specific parts of the datasets in order for you to just display that particular part of the dataset at any given time. And this can actually be quite useful if you do not want to supply and make visible a whole dataset to a customer, but really just pick out a specific region of interest and make that available to the customer. You clip it out and you create a web app from this particular view without modifying the underlying data model. So this means this operation can also be reverted at any point in time. No data is lost at any point in time. As you can see here on the top right, there is also the option to flatten certain areas of the mesh. That means we can even modify the view that we have of particular parts of the mesh in case that we want to involve it into urban planning and we want to actually plan a new building in a specific parts. We can just flatten it and plan the artificial building on top of it. The next use case showcases the draping capabilities that are available within ArcGIS Online. In this case, we have draped a layer that contains information about companies in Frankfurt on top of, so it's a polygon layer that has been draped on top of this integrated mesh. And by clicking on particular buildings, we can actually see the number of companies that are in this building in 2019. So we actually have attributes that can be accessed directly by interaction with those 3D buildings in the meshes, and we can see the attributes that are actually attached to the polygons for the specific buildings to the right side. And this really gives you the opportunity to just navigate in your 3D mesh model and then click on buildings and retrieve additional information for those buildings. Here we see another example of this. For example, in this building we have in the Euro Tower, we have actually 29 companies in 2019. So this really adds value and adds opportunity to not just assess geometrical and texture information and get a visual impression about the data set, but really also adds a new dimension by being able to access attributes and even more semantic information that is attached to these polygon layers that are draped on top of the integrated mesh. This concludes my talk for today. I want to thank you for your attention. I want to wish you exciting times on Dev Summit 2021 and continued success.